Hello, my name is Claudio Rodriguez. I am the chairman of the Technical Committee on Ocean Engineering. So in this session, I will be presenting our final report of this committee. The term for this meeting started in 2017 and go until this year, 2021. The members of my committee are Professor Longfei Xiao from Shanghai Jiaotong University of China, Rai Hyun Jak from Samsung Heavy Industries, Korea, Professor Kim Xiao from the University of Strathclyde, the United Kingdom, Vyacheslav Magarovsky from Krylov State Research Center in Russia, Halvor Lee from Sintef Ocean, Norway, Ayhan Mentes from Istanbul Technical University, Turkey, and Professor Yasunori Nihei from Osaka Prefecture University in Japan. So I will be making this presentation on behalf of all the members of our committee. So I have just presented all the members of our committee. So the meetings we have were basically two in-person meetings, one in the University of Strathclyde in 2018, and another meeting at Samsung Heavy Industries in Daejeon, Korea in from September 12 to September 14 in 2018. Due to the COVID pandemic, our scheduled meetings for 2020 were canceled, so that the last stage of coordination of the tasks has been done online. The outline of this presentation is basically focused on the task assigned by the 28th ITTC conference. I will then go into the structure of our final report and then go point by point on the task of the assigned by the 28th ITTC conference. And finally, I will make some conclusions, some recommendations. So I will just start making a review of the task assigned by the 28th ITTC. So task number 1 was to update the state of the art for predicting the behavior of bottom-founded or stationary floating structures, included moored and dynamically positioned ships, emphasizing developments since the 2017 ITTC conference. Our second task was to review the ITTC recommended procedures relevant to ocean engineering. Review the state of the art in offshore aquaculture system was our third task. And just concerned with deeper water, farther from shore, not in sheltered water, so offshore aquaculture, in fact, including harsher conditions, larger volumes, scaling of wall structure versus scaling forces acting on nets. Our fourth task was a review of the state of the art in model test of cable and pipe dynamics close to the sea surface. And task 5 was concerned about the review of the state of the art in hybrid testing, software in the loop tested for modeling wind forces. Task number 6 was concerned about extending the experimental wave run-up benchmark tested with 4 square vertical cylinders to measure wave run-ups and global forces on cylinders to investigate scale effects. Task number 7, carry out CFD benchmark study on two-body interactions, focusing on the investigation of viscous effects on the gap surface elevation, based on the benchmark experimental results of the last ITTC conference. Task number 8 was a review of the state of the art for large diameter flexible risers used for deep water mining. And finally, task number 9 was to rewrite model construction procedure with focus on model construction issues like material tolerances, production methods, quality control, and acceptance testing. So now let's go into the structure of our final report. So the final report basically follow the tasks that were assigned to our committee. So from section 2 to section 10, we go from each of these tasks, and we finish with section 11 with conclusions and recommendations for our next ITTC conference. So let's start with our first task that was concerned about the state-of-the-art reviews in offshore structures. So we have divided this state-of-the-art review in basically 3 sections. One concerned about bottom-founded structures, another with stationary floating structures, and a third one dealing with dynamically positioned floating structures. The focus of this state-of-the-art was to highlight new technological developments, new experimental techniques and extrapolation methods, practical applications of computational methods to prediction and scaling, and need for research and development for model experiments, numerical modeling, and full-scale measurements. Concerning bottom-funded structures, most of the papers that we have reviewed during the review period from 2017 to 2021, many papers were concerned about life extension of existing fixed platforms. Some of these platforms have already exceeded their design life, and the concern was on fatigue and vessel impact loads on these kind of structures. Earthquake loads have been also of concern, especially for the design of offshore wind turbines. So as new platforms for these applications are being used, and some of these the locations for the installation of these platforms move into regions where earthquakes are common. So this kind of analysis have been of concern. Foundations, of course, continue to be a concern for these structures, and there have been some works on the investigations of score processes, collisions, geotechnical issues, and some proposals have been made in terms of how to improve these foundations for these structures, like we see in our left side figure. On the right hand side, we have some numerical analysis made in terms of collisions and how these collisions may affect also the foundations of these bottom-founded structures. In concerning the stationary floating structures, we have made a review of the state of the art, subdividing it in the different types of floating structure, like FPSO vessels, semi-submersibles, TLPs, spar platforms, floating liquefied natural gas production, storage, and offloading vessels, FLNGs, and finally floating offshore wind turbines. So regarding FPSOs, several experimental and numerical studies have been published on green water and wave impact events, especially under extreme wave conditions. These works were concerned about CFD simulations, motions, impact load, wave elevations on the deck, as we see on the bottom figure, where we have some model tests concerned about green water on the deck. And on the right side, we have some CFD simulations of this same type of FPSO. Side-by-side configuration regarding wave elevation in the gap, shielding effects, horizontal and vertical forces have been also a concern of these FPSOs, as well as slow yaw rotations with wind-induced damping, low-frequency drift forces. Roll damping continues to be issues of this type of related to this type of platforms. In the case of semi-submersibles, there have been several works concerned about CFD studies, a few model tests on vortex-induced motion. So this is just to highlight several works different from the previous term of the ITTC conference. Several works have been devoted to the study of this VIM. So effects of column shape, column corner shapes, column steps, pontoon shapes, use of helical strikes have been some of the issues that have been addressed related to VIM. Besides the typical concerns like motion responses, wave impact, several other issues associated to the commission processes, float over installations, loading due to ice conditions have also been published during this term. Regarding TLPs, responses under extreme wave conditions have been some of the topics that have been addressed in the study of this type of platforms, especially concerned about wave index events, maximum and minimum tendon tensions, air gap, and so on. Interaction effects with other bodies, like when we have configurations of tender-assisted drilling, gun wave connections, multimodal behaviors, and the challenges continue to be the modeling of tendons, modeling of risers, modeling hawsers of these that connect this type of structures. In the case of spars, we have identified a work that presented a new concept that is called Spar Drilling Production Storage Offloading Platform, SDPSO, for ultra deep waters. And the main, as the name already says, it has the feature that storage capacity of this platform. Numerical and experimental studies on typical issues like couple spar mooring system responses under wind, waves, and currents have been addressed in several works. Slow drift motions, VIV, VIM under harsh environments, parametric motions have also been some of the topics that have been also concerned with this type of floating structures. In the case of FLNGs, experimental and numerical investigations on the effects of inner tank sloshing on motion responses. Also, side-by-side configurations continue to be an issue on this type of structures, especially on addressing loads on connections, large low frequency responsive, gap wave responsive, sloshing effects, mooring lines, and fenders responses have been of some topics that have attracted attention on this kind of platform. And finally, in the case of floating offshore wind turbines, several works have been identified dealing with model testing and numerical simulations to basically study couple effects about hydrodynamics, and servoelastic models using potential flow, nonlinear hydrodynamic responses, and also uncertainties have been addressed in this kind of structures. A real-time hybrid model that has been also one of the tasks of this of our committee have also been a topic that have attracted much attention, especially to simulate rotor and tower loads and the software in the loop approach for aerodynamic forces. Wind farms, for example, using an array of submersibles have also been one of the works that seem relevant for the development of this type of structures. And also we have identified one paper addressing a new concept, which is a monopile wind turbine wave energy converter. So it's, as the name says, it's a combination between a wind turbine and a wave energy converter. On the side of dynamically positioned structures, DP structures, several works, many works have been concerned with this type of floating structures, and especially in the application of DP to actual systems, such as the commissioning, heavy lift operations, to study this type of operations using DP vessels. The new algorithm for DP control system, including thrust allocation, control logic, and the integrating system, have been actively researched. Thrust and thruster hull interaction, and thrust deduction continue to be a major research topic. And we have identified also a specific concern with the study of DP vessels in environments with ice. So this is a topic that is appearing to be of much concern. With this we finish our task number 1, and then we go into task number 2 that dealt with a review of existing procedures. So we have reviewed with the following guidelines and procedures. So floating offshore platform experiments, analysis procedure for model testing regular waves, also for analysis procedure model testing in irregular waves, our procedures for model tests with active hybrid and passive hybrid mooring lines, mooring systems, dynamic positioning system model experiments, guidelines for VAV, guidelines for VIM, and also the guideline for model tests of multibodies in close proximity have been the procedures that have been reviewed by our committee. On task number 5, we will of course discuss most of these conclusions of these procedures in the conclusions of this report. So the next task dealt with a state-of-the-art review in offshore aquaculture systems. So first we started trying to identify what is the definition of an offshore aquaculture system, and we found in the work of Wang et al. In 2019 that offshore fish farming is defined as the fish farming that is performed in unsheltered waters, defined by the sea space outside a straight line joining 2 major capes within 25 nautical miles from the shoreline for economic feasibility. Within one of the other features for the classification of an offshore fish farming is water depth greater than 3 times the cage height and at least 15 meters between the cage bottom and the seabed for better dispersion of fish wasted. And a third characteristic for an offshore fish farm is that current speed ranging from 0.5 meters per second to 1 meter per second. And then we have also identified that fish farming worldwide is moving offshore, especially due to a lack of available nearshore production sites, where we have conflicts with shipping operations, fishing operations, tourist conservation and recreations. So to avoid this kind of conflicts, fish farming is moving farther offshore. Also, one of another reason for going offshore is a much larger sea space availability for these farms, and also better water quality that is essential for the production of healthy fishes. However, when these kind of structures move to offshore, many challenges have been rising, especially associated to more energetic environments or higher waves, winds, currents, and also inaccessibility of power supply and supporting services. We have made within our report a classification as suggested by one in open cage system and closed containment tank system. So this dividing this offshore aquaculture system in basically two major groups, one with open net cage system and one with closed containment tank system, which is more this is a more recent type of structures. Within the open net cage system, there is a classification in terms of the flexibility of the cages. So we have floating flexible cages, floating rigid cages, and also a subdivision between semi-submersible rigid cages and submerged cages. So we have a wide range of structures within this open net cage system. In the closed containment tank system, we have identified some concepts for this kind of structures that are discussed in detail in our final report. We have identified that fluid structure interactions between environmental loads and aquaculture cages is the major issue in these kind of applications, so that analytical, numerical implementations, field tests, laboratory experiments have been found and reported. Mooring and green systems, drag coefficients associated to the net panels, hydrodynamic behavior of these cage components and interactions with the main floating structures, velocity reduction due to cage arrays and volume reduction caused by cage deformation are also topics of concerns. And also we have identified some new concepts, for example, like the one showing in this corner figure, where we have a wind solar aquaculture system. So together with the fish farming system, we have coupled these renewable energy devices, in this case wind and solar systems. The other task we dealt was a state-of-the-art review in model tests of cable and pipe dynamics close to the sea surface. So this is the characteristics of this task was regarding these structures that operate close to the sea surface. And then we have identified some advantages compared to subsea pipelines, that, for example, we have improved flow assurance due to higher seawater temperature, so that we have reduced risk of blockage by formation of wax and hydrates when we have these pipes close to the sea surface. Also, another advantage is associated to the avoidance of seabed constraints, ground instability, irregular seabed profiles, subsea hardware congestion. So these are another reasons of benefits of this kind of applications close to the sea surface. However, we also have some disadvantages, especially in terms of limitation in the sizes, lengths, diameter, curvatures of these pipes or lines, strange and fatigue problems because they are close to environmental loads. So we have a stronger action of waves, a stronger action of currents close to the sea surface, and we also have some flow assurance concerns related to temperature drop, high cost of materials, installations. We have this problem of fatigue, interaction also with platform motions. So this type of pipelines operating in close to the free surface, they also have this strong effect associated to the platform motions and exposure to waves or higher current velocities, as I have already mentioned. So we basically divide this type of of review in fluid transfer lines, for example, pipes that we have some kind of fluid inside these lines, and especially used for some of the concerns with this type of application is VAV on offshore risers, on offloading lines, where effects of currents and waves, complex interaction with platform motions, because both lines ends are connected to floating platforms, use of helical strakes, effect of platforms, BIM have been issues concerned with this type of pipes that operate close to the free surface. We have identified some model tests addressing, for example, the depth of these pipes in relation to the free surface. Several studies have been also performed in terms of use of helical strakes to avoid VAV and so on. And in the case of cables, only few studies have been identified, and only numerical studies. There were not works concerning experimental studies on this type of cable. So for fluid transfer line, there are several studies associated to these model tests, but in terms of cable, we only found numerical works concerned about this issue, especially power cables for wave energy converters, towing cables, cables used for nets in the case of fish farming structures. And the main concerns were on responses of these power cables, including dynamic motion, curvature, cross-sectional forces, accumulated fatigue damage, and also the effects of environmental conditions on long-term mechanical lifespans. So one recommendation for the future of this kind is to perform experimental studies of this type of application. We only found numerical studies. Concerning the task associated to software in the loop tested for modeling of wind forces, we have, as we already mentioned in the state-of-the-art review for offshore structures, there have been identified several studies that dealt with this kind of approach for the modeling of wind forces, especially concerning floating wind turbines. So this SIL approach, so software in the loop approach, the objective is to use realistic force to represent aerodynamic forces on the turbine in the model testing of floating wind turbines. So the idea is to substitute the wind turbine scaled rotor with adapted fan, and then the fan thrust is controlled by a controller varying, for example, the rotational speed of the fan. And also fan thrust depends on a computer real-time simulation, considering platform motions measured in real time in the wave tank test, as reported in the work of Mueller and others in 2014. As Kohn et al., as we see in this figure on the right, presents a scheme of how this software in the loop approach works. The advantage of this software in the loop approach is that compared with traditional model tests, the tested here do not require a wind generation system. There is no requirement to construct a scaled model rotor and drive, so that the scale of the tests is detected only by the hydrodynamics of the floater, which in this case allows a test at a relatively large scale. The test procedure can replicate turbulent or steady wind in a variety of directions relative to wave heading. The impact of turbine control system and blade elasticity may be modeled also, and correct simulation of aerodynamic drag load on the tower and parquet turbine in extreme conditions is possible, and some special cases such as emergency stop tests can be simulated with correct fuel scale behavior. So several advantages have appeared as a consequence of the application of this software in the loop approach. So we have performed a review of these of the works related to this approach, and we have found that wind tunnel testing is used to model the behavior of floating wind turbines. The impact of platform motions on the turbine performance is simulated usually using 6 degrees of freedom PKM exaglide robot, for example, as in the work of Bayati et al. That we see where we see a scheme on the right side of this slide. A 5 megawatt spark void floating wind turbine was analyzed to verify the reliability of the robot to reproduce the dynamics of nominal operating conditions. The work of TIST and others presented a real-time hybrid model tests that it's called re-THM tests that were performed, for example, with a 10 megawatt semi-submersible floating wind turbine in an ocean basin. The wind turbine tower and the rotor were modeled by NREL fast and used to compute aerodynamic loads on tower. The test results of this as all has shown that the wind turbulence played an important role for the surge and pitch responses, especially at low frequencies. Hybrid wind tunnel and ocean model, basin model tested with floating offshore wind turbines were also performed as reported in the work of TIS and others in 2019. And then in the ocean basin, a physical model of this floating wind turbine without the rotor geometry was placed in the basin and coupled to a force actuator controlled by the simulated aerodynamic loads. The results indicated that the linear response to a small to moderate wave excitation is accurately modeled, but calibration of the numerical model is needed for accurate modeling of the low frequency response. So the work of Ascona and others have presented a first validation of this approach, coupling in real time the rotor simulation that controls the fan with the measured motions of a 6 megawatt semi-submersible scale floating wind turbine. So the platform design and assessment of the software in the loop system was verified, and the effect of wind over pitch motion was very accurately captured, which is important to calculate the correct rotor loads. There have been other works, such as the works of Zamora and Rodriguez, Sauder et al., the works of Date et al., August et al., that also, for example, using a TLP floating turbine, many other works that have addressed this software in the loop approach for modeling of wind forces. Well, our next task dealt with experimental benchmark of wave run-up cylinders. So the objective of this experimental benchmark was focused on the interaction between waves and fixed column array with 4 rounded square columns. And the objective was to investigate the influence of wave parameter, including wave stiffness, and wave period on these run-up events. It's important to mention that this experimental, a similar experimental benchmark has been performed previously, but using circular columns. Now we have an experimental benchmark with square columns. So model tests that were performed as part of the test campaign of this 29th ITTC Ocean Engineering Committee task. And a corporative study has been begun with tested at the State Key Laboratory of Ocean Engineering at Shanghai Jiao Tong University in China. We, due to the pandemic, it was difficult to coordinate other sets of experimental campaigns with other participants, but at least we have this experimental campaign performed at China. The experiment target, as I have already mentioned, it was a fixed column array with 4 rounded square columns. 3 wave steepness and 4 wave periods have been tested. This is these conditions were defined in order to keep an analogy with the previous circular column benchmarks, and the experimental site that we have used for the results that we will present it in the next slides are the results from the Shanghai Jiaotong University that were performed at the multiple function towing tank. So we have on the right hand side here the different environmental conditions that were performed, basically regular waves. And the test setup basically consisted in exploring 2 wave incident angles, 0 degrees and 45 degrees. So the layout of the text for the 0 degrees incident angle is performed here. We have here the wave generator, and then we have this 4 column array. We have 3 component force sensors were installed on each column, and also wave proofs on the columns were also used. This is the setup for the 45 degree wave incidence, also with the same experimental measurements. The details and discussions on these results are discussed in our final report, but then we can make here summarize some of the results. So that the wave run-up ratio increases with wave steepness, and especially for long wave, the steepness effect is even more pronounced. For 0 degree cases, the wave run-up ratio around the rear column is smaller than around the front column. In the case of 40 degrees incidence, these results are opposite. The force in the X direction in the 45 incident direction is greater than at 0 degrees. And also, as the wave steepness increases, the force difference between 0 degrees and 45 degrees wave incidence angles becomes obvious. So some of the conclusions of this experimental benchmark was that model test results show the effect on wave run-ups on fixed column array for different wave steepness and periods. The wave run-up ratio increases with wave steepness and is even more pronounced for long wave. For 0 degree cases, the wave run-up radio around the rear column is smaller than around the front column, while for 40 degrees, these results are opposite. The incident direction has a great effect on wave run-ups and the force on columns. And as a recommendation, CFD studies are required in order to establish procedures not only for the simulations in CFD, but also to support model test procedures for this kind of configuration. Well, another task that our committee dealt was with a CFD benchmark study for two-body interaction. So the objective of this CFD benchmark was to carry out numerical simulations on multiple body interaction in regular waves using the experimental results with 2 identical floaters in close proximity that were performed by the previous Ocean Engineering Committee. So the model tests were performed as part of the test campaign of the 27th and the 28th ITTC Ocean Engineering Committee. And the benchmark studies used various CFD softwares and methodology to produce the best solution for the two-body interaction problem. This was a cooperative studies. We at this at this stage, we have the participation of three institutions, so Samsung Heavy Industries, Korea Research Institute of Ships and Offshore Engineering, and the Busan National University Laboratory. The benchmark test case is described in detail in the 28th Ocean Engineering Committee report. So there is a description of the experimental benchmark with all the cases that have been investigated. Two box-like models have been used, as we see in the photograph in the upper part. These structures have a rounded bow and a rounded stern, and the calculation items that were used in the CFD and compared with the experimental results were 6 degrees of freedom motion, wave gap elevation was also measured, mean wave drift forces, and we have explored three gap distances, so 0.44 meters, 0.45 meters, and 0.55 meters of gap separation in model scale. Okay, regular waves at head seas have been the environmental condition that have been used. So the setup adopted in the experimental benchmark was the one shown here in this part, and the same setup was reproduced numerically. So several methodologies have been adopted by each facility in order to reproduce this setup. I won't go within each point, but then we can go to in the final report to have the description of each of the methodologies adopted for the facility. In the case of Samsung Heavy Industries, the CFD analysis was performed using a star CCM plus. The numerical modeling was performed, and the boundary conditions have been established as described in the tables shown here. Some of the more interesting results are regarding, for example, motion in 6 degrees of freedom, gap elevation, and drift forces. In the case of motion, viscosity effects due to two-body interaction, it is concluded that this effect is small, as we see here in the pictures, where we have here showing for this search RAO, heave RAO, and pitch RAO. So all these three show that viscosity effects on these motions is small. And how do we arrive to this conclusion? Just comparing CFD model tests and also potential theory numerical calculations. In this case, hydrostat have been used as the potential model. In the case of mean drift force and gap wave elevation, CFD compare well with model test results, but then we have here seen that the potential calculation deviated from model test and CFD results. So the conclusion is that viscosity affects drift force and gap wave elevation with a strength higher than the one observed in terms of motion. So some of the discussions regarding this, the results of the CFD benchmark studies, is that model tests and CFD results allow it to investigate viscous effects on motions and drift force on the bodies, and the gap wave elevation by comparison with potential results. Viscous effect on body motion is the smallest, but is the largest effect on wave elevation in the gap. viscous effect is more pronounced at higher wave frequency region. The smallest gap distance that was adopted was 0.40 meters, showing that largest viscous effect are present, while at the largest gap distance, negligible viscous effect was observed on body motion, drift force, and wave elevation. One of the recommendations is that further CFD study is needed by the various participants to establish the CFD procedure for this kind of configuration, and to also update two-body model test procedure based on this benchmark CFD. Well, let's pass now to our task regarding the state of the art reviewing large diameter flexible risers for deep water mining. So basically, we have reviewed the background that we have where for this kind of application, rigid pipe transporting systems are used for these large diameter flexible risers, flexible riser for transportation systems, and also flexible hoses with buoyancy materials. So these basically with these three applications of large diameter flexible risers have been identified within deep water mining applications. So flexible risers or hoses are commonly used to cater the varying water depth, the seabed topography, and the movement of the mining vehicle. The major challenges of these applications are pressure loss of the mixture inside these risers, the dynamic responses and spatial configurations of the risers, and also flow assurance issues are related to these kind of applications. So in the case of the first issue, which is pressure drop inside flexible risers, there is a problem. The problem definition is that pressure drop of the mixture determines the pump head and the energy consumption, and is affected by many factors such as particle size, particle density, solid volume fraction, flow rate, spatial configuration of the risers. And the main research methods that have been identified are experiments and numerical simulations. We have identified relevant references between 2001 and 2007, and these have been discussed in our report. The second challenge or topic that is important in this under this application is dynamic response and spatial configuration. So the idea is that reliable experimental and numerical methods are required to predict nonlinear geometric deformation and tension on the flexible risers, especially under complicated sea states and operating conditions of the mining vehicles. Again, the main research methods identified have been experiments and numerical simulations, and the relevant references are provided between 2005 and 2020. And finally, the third research topic has been flow assurance issues, where the research points identified were dynamic performance of minerals in the risers, flow correlation, validation, and abrasion tests, pipe wear under hydraulic transportation, and where the variables are the pipe materials and pipe inclinations, comparison of CFD results with test results for predicting erosion rate, and the relevant references have been identified a time span between 1978 and 2019. Okay. And finally, our last task was concerned about initially a procedure for model extraction, and we have inherited from the 28th Ocean Engineering Committee the development of a preliminary version of a procedure for the construction of offshore models. But then, after the comments from the advisory committee of the 28th ITTC, and also the recommendations from the AC of the 29th ITTC, the committee developed not a procedure, but a guideline for this model construction of offshore system. As basically because it is impossible, or it is not very practical to establish rigid procedures for this kind of operations. In this kind of applications of offshore systems, it depends on we have several problems that need to be addressed individually. So an offshore system can be composed. We have divided this guideline. We have started this guideline by defining an offshore system as composed by a bottom-founded or stationary floating structures, together with their mooring lines and risers or umbilicals, dynamic position devices, or any other auxiliary structural equipment involved in offshore operations. So what we have addressed is the model construction of the whole offshore system. The purpose of the guideline was to ensure the correct design and manufacture of the model of the offshore system for its testing in towing tanks, wave and current basins, and or wind tunnels, excluding from the scope of this guideline the field tests. So the key elements that were discussed in the procedures include model design, manufacture, and preparation of the model tests, and also the uncertainty analysis and the documentation of this model construction. So an offshore system model may include, as discussed in our guideline, the hull and the buoys, appendages, surface roughness, marine growth, mooring system, risers and cables, offloading system, including hoses and fenders, dynamic positions and other control systems, thrusters and propellers, turrets, superstructures, sloshing tanks, and also energy conversion systems such as wind turbines, current turbines, and wave energy converters. So just to close our this presentation, we go now into the description of the main conclusions and recommendations. So regarding our first task that was concerned with the state-of-the-art review in offshore structures, we can conclude in terms of bottom-founded structures that life extension of existing fixing platforms have attracted much attention. Fatigue and vessel impact loads are the main concerns. For fixed offshore wind turbines, besides waves, wind, current, and loads, earthquakes load have become an item of concern. There is a need, of course, of full-scale tests for validation studies, because most of these studies are performed numerically. There are only few model tests results that have been published, so there is a need for full-scale validation of these kind of applications. In the case of floating structures, several experimental and numerical studies have been devoted to green water and water impacts associated to extreme wave. Side-by-side configurations and viscous damping are issues that continue to attract much attention for FPSOs and FLNGs. In the case of TLPs, semi-submersibles, and floating offshore wind turbines, several works have been devoted to VIM. Operations under ice conditions have also attracted much attention and deserve further experimental and numerical research. Regarding the state-of-the-art review in offshore extractions and the new technological developments, we have identified that a hybrid foundation proposed by Cheng and et al. For bottom-founded offshore wind turbines, a design method for topology optimization for jackets and other fixed structures was proposed by Tian and others. Liu and others have described the new concept of this spar drilling storage offloading platforms for ultra-deep waters. Ren and others have presented a new concept for the MWWC, so the monopile wind turbine wave energy converting combination. And Fu and others have proposed a new concept to remove large and heavy structure with a single lift, utilized using 3 semi-submerged DP vessels. And these are mainly the technological developments have been identified within this time frame. In terms of new experimental techniques and extrapolation methods, we have identified a creative method for equivalent design of an oil offloading line for model tests. PARC have proposed a new experimental method for the assessment of towing and course stability of a FPSO towed by a tugboat. In terms of practical applications of computational methods for prediction and scaling, Liu have developed and others have developed a novel multi-body dynamic mathematical modeling for soft yoke mooring system of FPSOs. Coop have used CFD simulations to address Reynolds scale effects and shielding effects on current loads of offshore structures in side-by-side configuration. And Wang and Su, in his latest work, they have carried out numerical simulations and experiments about the scale effect of internal solitary wave loads on Spark platforms. In terms of offshore aquaculture, offshore aquaculture systems have been concentrated on the development of large floating structures. Closed containment tank systems have been proposed to avoid effects of sea lice on fish. Hydrodynamic interaction among the main floating structure, the mooring system, and the fishing nets continues to be a concern, especially under harsh environmental conditions. So that more physical model tests, numerical simulations are required to study the effects of swimming of fish on the selection of farming sites and on the designs of offshore aquaculture cage systems. Fluid ice aquaculture structure interaction must be studied for aquaculture cages deployed in regions where drift ice could damage cage structures. So this is a topic for future research. And integration of offshore aquaculture farming and ocean renewable energy system should be further developed and studied. Cable pipe dynamics close to the sea surface. So our main conclusions and recommendations are that we have identified few experimental studies on these topics. Most published works are concerned with fluid transfer lines, such as risers of loading hoses. But we have not found a model tested, for example, to study cables, for example, power cables used with ocean renewable energy conversion devices. So this is a topic also that should be much studied in terms of numerical simulations, but there is lack of model tests. Behavior of offloading hoses in the gap of side-by-side configuration should be further investigated also. In terms of software in the loop tests, this approach offers a number of advantages over conventional full couple modeling, and the ability to deploy in a wide range of facility, reduced cost, greater flexibility of scale, and ability to simulate control system are within the main advantages of this approach. This system is still under development, and there are some issues with respect to repeatability and experiment methodology that require further refinement. Regarding experimental benchmark on wave run-up on cylinders, we have identified that benchmark tests were conducted to measure the wave run-ups and global wave loads on fixed form square column cylinders, and the regular and irregular wave. Local wave impact loads on the columns are critical, and they deserve further in-depth studies. In the case of the CFD benchmark performing for the study of two-body interactions, viscous effect on body motion is the smallest effect, but shows a larger influence in the gap wave on the gap wave elevation. Viscous effect is also more pronounced at higher wave frequency regions. The smallest gap distance that we have used was 40 centimeters, which is equal to the mean of the model, showed the largest viscous effect, while the largest gap, which was 0.55 centimeters, 0.55 meters, sorry, showed negligible viscous effect on the body motion, drift force, and gap wave elevation. So one of the recommendations is to continue studying this problem, but with smaller gaps, smaller than the beam of the model. Regarding large diameter flexible risers for deep water mining, technologies for the design of flexible risers are not firmly established yet. So owing to complicated interaction of flexible risers, the inner flow and environmental loads, the couple analysis of the inner flow regime and external loads are rare, so they deserve further research. Aggregation and clogging of the ores in the flexible riser should be investigated in detail due to the complex flow regimes and particle motion when the mixture flow is passing the crest and through of curved risers. So it's something that also deserves further research. And regarding the recommendations to the 29th ITTC, is to adopt procedure for the review with procedure for floating offshore platform experiments, to adopt the review where the updated procedure analysis procedure for model tests in regular waves, also to update the procedure for active hybrid model tests of floating offshore structures with mooring lines, to adopt the updated procedure passive hybrid model tests of floating offshore structures with mooring lines, and adopt the updated procedure dynamic position system model experiments, adopt the updated guideline for VAV testing, adopt the updated guideline for model tests of multibodies in close proximity, adopt the updated guideline for VIM testing, and also to adopt the updated procedure for analysis of model tests in irregular waves. Recommendations for future work. Since in the recent years, a number of numerical and experimental works have been reported on side-by-side configuration and on VIM, the following procedure should be reviewed and updated accordingly. So since there have been several works concerned about side-by-side configuration and VIM, we are recommended to for the next committee to continue updating and improving the model tests of multibodies in close proximity and the guideline for VIM testing in order to incorporate these new developments. Follow the development on offshore aquaculture system, especially on model testing and numerical modeling. Hydrodynamic modeling of loads on the nets due to fish swimming, wave, and or current should be further investigated. Sloshing in closed containment tank system should be also of concern. And regarding the experimental wave runnage benchmark test, the idea is to continue this benchmark test with the 4 square vertical cylinders to measure wave run-ups and global forces on cylinders and to investigate scale effects. The participation of more institutions should be encouraged, and results should be further analyzed and compared with new data. Extend the experimental benchmark on two-body interactions to consider smaller gaps, so gaps less than the mean of the models. Continue the CFD benchmarks on two-body interactions to gather results from more participants, and also extend the CFD study to investigate configurations with the smaller gaps. And CFD results should be further analyzed and compared with the experimental results of the previous committee. Carry out CFD benchmark studies on wave run-up, focusing on wave run-ups and global forces on cylinders and scale effects using the benchmark experimental data. So the idea is to gather all the the experimental results obtained until now, and also perform now a CFD benchmark studies to reproduce the experimental configurations. And finally, owing to the complicated wave column interactions, more experimental and CFD studies on wave run-up should be carried out for different configurations of the 4 columns. More extreme waves, such as focus waves, should be also considered. And that's all. Thank you very much for your kind attention. And me, the chairman of the committee, and Professor Long Fei Shao are open to your questions. Thank you very much again. See you for the questions.